This SHD-CCP packet simulator is an interactive testbed for a concept at the heart of high-performance computing and data structure co-design. Our high-level goal is to find an Einstein packet, which is a stable, aperiodic, and self-organizing data structure that can tessellate indefinitely. But finding it is only half the battle. It's useless if it's too slow to compute. Therefore, this simulator was designed for one specific purpose: to test how our 64-bit SHD-CCP packet can be architecturally optimized to run with maximum efficiency on modern GPUs, specifically the NVIDIA H100. We aren't just simulating a pattern, we are simulating the performance of that pattern as it would map to the silicon. The fundamental challenge in all GPU computing is not math, it's memory optimization. A GPU can perform trillions of calculations per second, but it's often starved for data. In a simulation like ours, where the state of one packet depends on its neighbors, this is a critical problem. When a group of threads calculates the state of a packet, it inevitably reaches the edge and needs data from a neighboring packet. In a simple design, that neighbor's data is far away in slow global memory. This read operation can stall the entire compute core, wasting thousands of potential calculations. This is where halo and ghost regions come in. Instead of fetching one piece of data at a time, a high-performance kernel prefetches the entire edge of its neighboring data, the halo, and copies it into its own super-fast local memory before it starts working. The data you put on the edge of your packet is the only data your neighbors will see in this high-speed exchange. This is the single most important design constraint, and it's what our simulator is built to optimize for. The NVIDIA H100 introduces a new feature that maps perfectly to our simulation: the thread block cluster. This is how our simulator models the H100's architecture. The 9-core grid. This represents a thread block cluster, a new H100 feature that allows 9 separate thread blocks to be scheduled together and cooperate. Each 8x8 core. This represents a single thread block, which is 64 threads, or 2 warps. These threads are responsible for processing one 64-bit SHD-CCP packet. The Halo/Ghost view. This is our direct visualization of the Distributed Shared Memory, DSMEM. This is the high-speed, 7x faster memory link that allows the 9 blocks in our cluster to share data without going to global memory. Our entire goal is to design a 64-bit packet layout that takes maximum advantage of this hardware. We are optimizing for 3 key H100 features. First is optimization of the Tensor Memory Accelerator, or TMA, which is a new hardware unit on the H100 designed to asynchronously move large, continuous blocks of data, like tensors or quaternion blocks, from slow memory to the fast shared memory. Our layout is TMA-friendly. This means a kernel can issue a single asynchronous TMA command to load the entire quaternion while the threads are busy doing other work, like processing the halo data. Next is the optimization of the Distributed Shared Memory, or DSMEM. The data that lives on the edge of our 8x8 grid is what will be exchanged via DSMEM. We must place our most important communication bits there. For most cases, the 4-bit structural form ID and the 1-bit parity right on the packet's edge. This means when our 9 cores talk to each other, they are only sharing the 5 most critical bits needed to determine their collective behavior. The third optimization is a field-weighted simulation with tensor cores. This allows mixed precision training and matrix mathematics to be extremely fast. These tensor cores are specialized and can apply different rules and data types, like FP8 versus FP16, based on the task. We can use these to give heavier weights to the bits we've defined as important. For example, bits mapped as structural form ID are stickier, more likely to survive, while parity bits are volatile, less stable. By intelligently laying out our packet to leverage the TMA and DSMEM, we can create a system where the interaction of these specially weighted edge bits, the form ID and parity, gives rise to a stable, complex, and aperiodic tiling. This tool allows us to stop guessing. We can modularly and visually design, map, and test our 64-bit SHD-CCP packet structure against a model that respects the real-world hardware constraints and optimizations of cutting-edge GPUs. We are finding the Einstein packet by co-designing the data and the algorithm to be perfectly aligned with the hardware it will run on.